Hey guys, I'm Jake. Today is my LeetCode review vlog on 146th problem, LRU Cache. We have to design a data structure that follows the constraints of a least recently used cache. We have to implement the LRU Cache class for three methods. The first is the constructor method to initialize LRU Cache with positive size capacity, and the get method to return the value of the key if the key exists, or just return -1, and the final put method to update the value of the key if the key exists. Otherwise, we'll add the key value pair to the cache. And the get and put method must each run in big O1 average time complexity. Then, let's get started with our intuition to solve the problem. And the keyword is hash map and doubly linked list. We'll create a hash map to store the key value pairs, which can provide big O1 average time complexity for the get method and the put method. And we also have to create a doubly linked list to keep track of the order of usage. The most recently used item would be at the head of the list, and the least recently used item would be at the tail. This would allow us to quickly move nodes to the head on the get method, and remove nodes from the tail when the capacity is exceeded. Then, let's get started with our code and annotations to solve the problem. The very first step, we'll create a node, and the node represents each entry in a doubly linked list. And it has several variables here, let's say key and value. Then we have to create two pointers, the previous node pointer and the next node pointer. We also have to implement this constructor method, and there are two input parameters. The first is a key, int key, and the second is the value. This dot key equals key, this dot value equals value. And that's all of code for the class node. And we also have to create several variables for the class LRU Cache. The first is the capacity we need, private final capacity. And the second is a hash map, private final map of integer and a node. And we also have to create two dummy nodes to represent the head and the tail of the doubly linked list, which can help us simplify the insertion and removal operation. Private final node, the head node and the tail node. Next, we have to implement the LRU Cache constructor method with initialization code. Inside the constructor method, first we have to capacity. We have to update the capacity got from the input parameter, and then is the map variable equals new hash map capacity. Next is the two nodes. The head node started at a node of 0 and 0. Oops. And the tail node is very similar. Tail equals new node of 0 and 0. And we have to make the next pointer of head node points to the tail. Oops. Points to the tail. And the previous pointer of tail node, previous, equals points to the head node. And that's all of code for the LRU Cache constructor method. And then we have to implement the get method. First, we have to retrieve the node for the given key from the map. Node equals map.get key. Get key. And there are two cases. If the key is not found, we just return -1. And the code is if node equals null, we just return -1. And for the second case, if the key is found, we'll move the access node to the head of the list to mark it as the most recently used node. Let's create a new private method called remove node. And we'll implement the remove method in the following code. So we just skip it right now. And the second step, we also have to insert the access node at the head of the double linked list because we just visited right now. Insert to head of node. And the final step, we just return the value that it wants. Return node.value. And that's our code for the get method. Next, we have to implement the put method, which is a bit more complicated. First, it's very similar. We have to get node map.get of key. If the key exists, we just update the value and move the node to the head of the list. If node is not equal to null, first we have to update the value of node equals the new value and move the updated node to the head. But the first step, we have to remove from the double linked list. Remove the node first, and then we'll assert a new node at the head of the double linked list. Insert to head of node. And on the other hand, if the key does not exist, we have to check the capacity. And if the cache is full, we have to remove the last recently used node from the tail. And the code is map.size is bigger than or equal to capacity. If so, first we have to get the reference of the last recently used node so we can remove it. Node LRU node equals tail node.previous pointer. Then we have to remove the node LRU node. Remove the LRU node from the doubly linked list. On the same time, we also have to remove the node from the map. Remove LRU node.key. And after removing the last recently used node, we can add the new node to the LRU cache. And the code is first we have to create a new node with new node of key and value. Next, we'll put the new node into the map. Map.put key and new node. We also have to insert the new node at the head of the doubly linked list. Insert to head of new node. And insert to head method is also a new private method we have to implement in the following code. And that's all of the code for the put method. And in the following step, we have to implement the remove method and insert to head method. Let's implement the remove method first. And input parameter is a node. First, we'll make the previous node of the input node's next pointer point to the next node of the input node. Node.previous.next equals node.next. Oops. Node.next. Next, we have to make the next node of the input node's previous pointer point to the previous node of the input node. Node.next dot previous pointer equals node.previous. So we just remove the node from the double linked list. And for the final state, we have to implement the insert to head method. Insert to head method. And the input parameter is also a node. The first state, we have to make the input node's next pointer point to the next node of the new node. Node.next equals head.next. Second state will make the input node's previous pointer point to the head node. Node.previous pointer points to the head. And the third state, we have to make the next node of the head node's previous pointer point to the input node. Head.next node.previous pointer points to the new node. And the final state, we'll just make the head node's next pointer point to the input node. Next, head.next equals node. So the input node would become the unique new head node right now. And that's all the code for the insert to head method. Let's submit code and check for the correctness and analyze the time and space complexity. Capacity, oops, I forgot an integer here. Is here in capacity. Let's check it again. Yes, our code got accepted. And the time complexity, it is big O of 1, both for the get method and put method, because we have used the combination of the hash map and the doubly linked list. And the space complexity, it is big O of n, and n is the capacity of the LRU cache. This is because we stored up to capacity nodes and their mappings in the hash map. And thank you guys for watching. This is my LeetCode review vlog on this problem, LRU cache. And I highly recommend you guys to visit my online GitHub page here, which contains all the nodes for the top 150 LeetCode problems. And for each problem, you can see the problem description, intuition, Java code with annotations, and the final time and space complexity analysis. You can also visit my GitHub repository here, which contains the nodes and codes to build the online GitHub page here. And I'll put those two links on my YouTube description below. And thank you guys again for watching. And I'll see you next time. Bye bye.